This is the final problem solving session on engineering thermodynamics. So what we'll look at today is we'll look some problems on vapor compression cycle. So the previous session we looked at Rankine cycle and Brayton cycle. So the vapor compression cycle was remaining. So we'll see some problems on vapor compression cycle, and then we'll go through the concepts of the engineering thermodynamics course which was covered over the weeks. So I'll just briefly go through those concepts and see. So let's get started on the first problem for vapor compression cycle. So the first question is, we have R134A which enters the compressor of a vapor compression refrigeration cycle at 120 kilopascal as a saturated vapor and leaves at a 900 kilopascal and 75 degrees Celsius. So the refrigerant leaves the condenser as a saturated liquid. The rate of cooling provided by the system is 1000 BTU per hour. So which is British thermal unit. So we'll see how it's will convert. So then determine the mass flow rate of R134A, the COP of the cycle. Determine the COP of the cycle. The expansion value is replaced by an isentropic turbine. Do you recommend such a replacement for refrigeration system? Then determine the COP if the evaporator pressure is 160 kilopascal and other values remain the same. And then determine the COP if the condenser pressure is 800 kilopascal and other values remain same. So you have series of questions and modifications which are to be made. So first is, we have a simple R134A cycle which is operating between two pressure levels. So evaporator pressure is 1200 kilopascal and the higher pressure is 900 kilopascal. So those are the two pressure. So in a vapor compression cycle, so you have this you have two isomer process in the Carnot cycle. So those are replaced with an isobaric process, and you have two isentropic process, reversible isentropic. So in this case, the compression still remains as a isentropic process, but the expansion is converted to an isenthalpic process. Your enthalpy remains same. So that is its only change in a vapor compression cycle. So you have isentropic compression, reversible adiabatic compression, and then an isobaric heat rejection. Then there is expansion in valve, which is a constant enthalpy or an isenthalpic process, and then constant pressure heat addition. So this is your vapor compression cycle. So in this, the two pressure levels are 1200 kilopascal and 900 kilopascal, and we know the saturated vapor is the inlet to the compressor, and it leaves the condenser as 75 degrees Celsius and a 900 kilopascal. Sorry, the exit of your compressor is 900 kilopascal and 75 degrees Celsius, and it is coming out as a saturated liquid. So the cooling rate is provided. So from this we can find out the mass flow rate. So for that we'll find out first the COP, and then we'll replace the valve with the isentropic turbine and see how much is the COP and can we use it, and then we'll change the evaporator pressure from 120 kilopascal to 160 kilopascal, and similarly we'll reduce the condenser pressure from 900 kilopascal to 800 kilopascal. So these are the changes which we will make. So if you plot this vapor compression cycle in a TS diagram, so this is your vapor dome, and these are your two pressure levels, or in a pure fluid it boils at a constant temperature. So a constant pressure is also a constant temperature. So you have constant temperature here lying inside the dome, and then if you draw an isobar, so this is how it looks. So it extends, it will be close to the liquid dome, and then it enters the vapor pressure dome, and then there's boiling, and then at saturated vapor you are compressing it to 2s ideally, and then actually it will be 2, and then you are rejecting heat in the condenser, so the constant pressure heat rejection, and then from at saturated liquid you are expanding in the valve. It's an isenthalpic process, so there will be entropy generation. So 3 to 4. So this is the process. So we know the pressure levels 120 kilopascal and 900 kilopascal. So corresponding to this pressure level, we can estimate saturated pressure. What is the saturated vapor enthalpy at 1? So that is 236.97 kilojoule per kg. So this we will get it from the R134A table or chart. Then this saturated vapor is compressed in a compressor to a pressure of 900 kilopascal and a temperature of 75 degrees Celsius. So we know both pressure and temperature, and we know that this will lie in a superheated state. So the enthalpy corresponding to this pressure and temperature will give you is 310.51 kilojoule per kg. So that is your enthalpy at the exit of the compressor, and then this gas will be cooled down, so it will reject heat to the ambient, and from 2 it reaches a saturated liquid condition, which is at a pressure of 900 kilopascal. So we assume there is no pressure drop here. So it is 900 kilopascal and saturated liquid. So corresponding to this state, your enthalpy is 101.61 kilojoule per kg. So that is your enthalpy at state 3. And then we know in a valve you have assumed that kinetic energy and potential energy is 0, and there is no heat transfer and the work transfer. So what you will ultimately end up with is your enthalpy is constant in a valve. So it is an isenthalpic process 3 to 4. So your enthalpy will remain constant. So H3 is equals to H4. So now we have found out all the enthalpy values of each of the state points between the each of the components for the process. So we know all the enthalpy state points. So now we can calculate the COP. So we need to find out COP and how much is the mass flow rate. So if you find what is the specific work done, so per kg of fluid, what is the work done, then it is straight away the enthalpy difference. So H2 minus H1, because we assume that it's an adiabatic process. So your work done, specific work done is 310.51 minus 236.97. So that gives you specific work to be 73.54 kilojoule per kg. And then your cooling, specific cooling which is provided, so that is a specific amount of cooling provided in the evaporator. So that will be enthalpy difference here, H1 minus H4. So that will give you the cooling rate per kg of refrigerant. So H1 is 236.97 and H4 is equals to H3. So H3 is 101.61. So that gives you QLS 135.4 kilojoule per kg. So that is your cooling rate. And what is given is already how much cooling is provided by this refrigerator or air conditioner or vapor compression cycle. So here it says that cooling capacity is 18,000 British thermal unit per hour. So 3,412 British thermal unit per hour is 1 kilowatt. So if you divide it by 3412.14, we get how much kilowatts can convert. So that is equals to 5.275 kilowatts. So mass of refrigerant is 5.275 divided by 135.4 kilojoule per kg. So that mass comes out to be 0.039 kg per second. So that is your mass of refrigerant in the cycle. Next is the COP of the refrigerator. So COP is nothing but your desired output by your input. So your desired output is your cooling requirement here. So QL divided by W. So because mass will get cancelled out, we can write straight away in terms of specific quantities. So QL by W will be equal to 135.4 divided by 73.54 kilojoule per kg. So that gives you a COP of 1.84. So this is your COP when you are operating as a vapor compression cycle. Now if the expansion valve has to be replaced with an isentropic turbine, so what will happen in this case? So previously we know H3, and we know because it was a valve we found out H4 straight away, but now instead of 3 to 4 we have isentropic expansion. So from 3 it will reach state 4s. So there will be a constant entropy process. So entropy at 3 and entropy at 4s will be remain same, and then 4s we can estimate the quality using saturated liquid and saturated vapor entropies, and then use that quality to estimate the enthalpy at state 4s. So that's what we'll do. So if valve is replaced by isentropic turbine, so at saturated liquid out of state point 3, so you have pressure of 900 kilopascal and quality is 0, that is saturated liquid. So your saturated liquid entropy at that point is 0.3738 kilojoule per kg Kelvin, and P4 is 120 kilopascal. So we know that since it's an isentropic process, so your entropy will remain same. So S4 equals S3, so which is equals to 0.3738 kilojoule per kg Kelvin. So enthalpy at this point is now for this pressure and entropy, it is 92.98 kilojoule per kg, which we can get straight away from the chart, or we can estimate the quality first, and using that quality we can estimate the enthalpy, and it will come out to be 92.98 kilojoule per kg. So now in case of a valve we don't get any work output or heat transfer, but in turbine, since we are assuming it to be an isentropic turbine, we are getting work out, and Q out is 0. So your work which is produced in the turbine is equals to the enthalpy difference across the turbine. So per kg of refrigerant flowing in the turbine produces the H3 minus H4s amount of work. So that is 101.61 minus 92.98 gives you 8.63 kilojoule per kg. So this is the amount of work which is produced. So the net work which is supplied to the refrigeration cycle is, so compression consumes some work and some part of it is recovered in the turbine in case of when you are using a turbine. So the net work is the difference between the work supplied. So 73.54 is the compression work which is supplied minus 8.63 is the produced work in the turbine. So that gives you the net work to be 64.91 kilojoule per kg, and the cooling rate in this case is, you will have a higher cooling rate because H4 is 4s is lower than H4. So you have larger cooling rate, and in other words you have a lower mass flow rate requirement. So QL is H1 minus H4s, that gives you 144 kilojoule per kg. Here it was 135.4, which has increased to 144. So for the same cooling capacity requirement of 5.275 kilowatts, you will require a lower mass flow rate in this case. So the COP is now QL by W net, so which is equals to 144 by 64.91 gives you a COP of 2.21. So what has happened here is, replacing the valve with the turbine has caused a lower work input because you are recovering part of the work which is provided in the turbine. So your net work which you are supplying to the cycle has come down, and also your cooling rate has gone up. So QL has increased, and both your numerator is increasing and denominator is decreasing. So your COP will increase. So that's what you are seeing. So previously it was 1.84, now it has increased to 2.21. So the COP has increased by 20.1% by replacing the expansion value by a turbine. So thermodynamically this makes sense because your work is reducing, you are getting higher cooling capacity, and your COP is also increasing. So it's all in the favor of moving to a isentropic turbine. So however, the problem is it's not practical, as this will be not reliable because you are operating in a two-phase region. So it will not be reliable, and it will also cost more. So capital cost will also increase even if it is okay to go ahead with the turbine, but then your capital cost will be more because you have to operate a turbine. So next is, if the evaporator pressure is increased to 160 kilopascal from 120 kilopascal. So in that case what happens is your H1 will change, but H4 remains same because your H2 remains same, and H4 will also remain same because your state point 2, you are just moving this 1 to 4 a little bit higher. So 2 will remain same because that is the state point which is already given, 900 kilopascal and 75 degrees Celsius, and then 3 is also remain same, which is saturated liquid condition. So if that's the case, the only enthalpy term which is getting changed is the H1. So H4 is equals to H3, so H3 is remaining same, so that will remain same. So COP, if you write terms of enthalpy terms, so COP is the cooling rate divided by the specific work. So QL by W gives you H1 minus H4 divided by H7, H2 minus H1. So substituting the enthalpy values, so H1 is 241.12 in this case when your pressure is increased from 120 to 160 kilopascal. So the enthalpy is 241.12 and H4 is 101.61, which is same. So and similarly H2 is 310.51, you see 310.51, so only changes H1. So that gives you a COP of 2.01, you see. So increasing the pressure will increase your COP, and which is also true if you see when in a Carnot cycle. So if your temperature levels are reduced, difference in the temperature levels of the source and sink, your COP will increase. So that's what is happening here. You can see the same kind of trend. So increasing the evaporator pressure from 120 to 160 has increased your COP from 1.84 to 2.01, which is an increase of 9.2%. Next is, if the condenser pressure is 800 kilopascal instead of 900 kilopascal. So in this case what will happen is your both in enthalpy at 2 and 3 both will change, and it will affect enthalpy at 4. So calculating the same way, instead of 3 you are now using enthalpy of 800 kilopascal and 75 degrees Celsius and saturated liquid. So if we find out the enthalpy terms, so H1 is 236.97, which remains same, which is the 120 kilopascal saturated vapor enthalpy, minus the saturated liquid enthalpy corresponding to 800 kilopascal is 95.47, so that is H4, divided by H2 minus H1. So H2 is enthalpy corresponding to 800 kilopascal and 75 degrees Celsius, so that is 311.92, so minus 236.97, so that gives you a COP of 1.99. So decreasing the condenser pressure from 900 kilopascal to 800 kilopascal has not increased the COP by a lot, but it has increased COP to a percentage of 2.7%. So it has increased from 1.84 to 1.89, which is a increase of 2.7%. So with that, we have seen how a vapor compression system works, how the cycle vapor for a vapor compression system cycle works, and then we estimated each of the process, the values, and the COP of the cycle, and then we also see how the COP varies with changing the pressures and also by changing the process. So let's move on. So you have a simple refrigerant R134A heat pump for space heating, operates between temperature limits of 15 and 50 degrees Celsius. The heat required to pump in 100 megajoules per hour. Determine the dryness fraction of refrigerant entering the evaporator. The discharge temperature assuming the specific heat of vapor as 0.996 kilojoule per kg Kelvin, and C, the theoretical piston displacement of the compressor, the theoretical horsepower of the compressor, and E, the COP. So the specific volume of refrigerant R134A saturated vapor at 15 degrees Celsius is 0.04. The theoretical the specific volume of R134A saturated vapor at 15 degrees Celsius is, which is the inlet to the compressor, is 0.04185 meter cube per kg. The other properties are saturation temperature is 15 and 50, the corresponding pressures and the enthalpies of saturated liquid and vapor, and similarly saturated liquid and vapor entropies are given. So first is the dryness fraction of the refrigerant entering the evaporator. So that is your enthalpy at the evaporator inlet, which is equal to the condenser exit enthalpy, which we assume it to be a saturated liquid. So saturated liquid enthalpy corresponding to 50 degrees Celsius, because it's operating between the temperature limits of 15 and 50. Because pressures and fluid your pressures and temperature are constant. You have saturated pressure corresponding to saturated temperature of 50 degrees Celsius. So that is your pressure pressures in which it is operating. So the exit of this is 271.62. So that is your inlet to the evaporator, which is 271.62. So 271.62 minus your enthalpy of saturated liquid divided by the latent heat. So that gives you a dryness fraction of 0.274. Next is the discharge temperature. So discharge temperature, we assume the compressor to be operating as a isentropic compression. So it's a reversible adiabatic compression. So your enthalpies are same. So what you write is S1 is equal to S2. So S2 is nothing but your ideal entropy plus at the datum and with change in temperature. So S1 is S2 dash plus Cp ln T2 by T1. So S1 is 1.72, which is saturated vapor corresponding to 15 degrees Celsius, which is 1.72, and at S2, which is your saturated vapor enthalpy plus because your temperature is much higher than the saturated vapor enthalpy, you are in superheated region. So it is equal to S2 is equals to saturated vapor entropy plus the entropy change because of change in temperature, and because you are assuming constant pressure. So you'll get S2 dash plus Cp ln T2 by T2 dash. So we get 1.7072 plus your Cp is given as 1.246 multiplied by ln T2 divided by T2 dash is your saturated vapor temperature corresponding to that point. So which is 273 plus 50. So substituting this, can estimate T2. So T2 comes out to be 327.15 Kelvin, which is 53 degrees Celsius. So the enthalpy at discharge is your saturated vapor enthalpy plus Cp, the change in temperature. So the saturated vapor enthalpy corresponding to 50 degrees Celsius is 423.4 plus Cp is 1.246 multiplied by your temperature change. Your saturated vapor is 50 but your exit temperature is 53. So that gives you H2 as 427.2 kilojoule per kg. So that is your enthalpy at discharge. So now using this, you can find out how much is the mass flow rate, because the heating requirement is given as 100 megajoules per hour. So we know Q. So Q is 100 megajoules divided by 3600 divided by your enthalpy change. Since enthalpy is in kilojoules, we have written 100 megajoules in terms of kilojoules, which is 100 into 10 power 3 kilojoules divided by 3600, and your heating requirement is your top where your heat is getting rejected. Now in heat pump, 2 to 3 is your desired output where heat is getting rejected. So that is getting rejected into, or heat is used for heating in a desired room or space. So in cooling we are concerned with 1 to 4, but in heating we are concerned with process 2 to 3. So what we get is Q is m dot multiplied by H2 minus H3. So m dot is Q by H2 minus H3. So Q is 100 megajoules per hour. So 100 into 10 power 3 kilojoules divided by 3600 divided by H2 minus H3. So that gives you a mass flow rate of 0.179 kg per second. So that is your mass flow rate. Then we know mass flow rate. We need to find out the theoretical piston displacement of the compressor. So the piston displacement of the compressor is so volume is m dot into specific volume. So mass is 0.179 kg per second multiplied by specific volume, which is 0.04212. So that gives you 7.539 into 10 power minus 3 meter cube per second. So that is your theoretical piston displacement. Next is the power consumption. So power consumption is nothing but your work done. So is mass into change in enthalpy, because Q is 0 and negating kinetic and potential energy, that's what you get, m dot into H2 minus H1. So m dot we have found out, which is 0.179, and H2 minus H1, substituting the values, enthalpy values, we get work done to be 3.6 kilowatts. And then the heating capacity is m dot into H2 minus H3. So that comes out to be 27.9 kilowatt. So the theoretical COP is H2 minus H3, which is the heating capacity, divided by H2 minus H1, which is the specific work done. So that gives you a COP of 7.75. So the other way around, we can substitute the values which you have found out. So 27.9 divided by 3.6 is 7.75. So what it actually says is, for every 1 watt of work input, you get 7.75 kilowatts of heat. And that's what is written here. So for 3.6 kilowatts of power, we get 27.9 kilowatts of heat. But in case of electric resistors, if you are using for heating, you get 1 kilowatt input, you get 1 kilowatt of heat. So next is we have a refrigerator using R134A as a refrigerant is used to keep a space at minus 10 degrees Celsius by rejecting heat to ambient air at 22 degrees Celsius. So R134A enters the compressor at 140 kilopascal at a flow rate of 375 liters per minute as a saturated vapor. The isentropic efficiency of the compressor is 80%. The refrigerant leaves the condenser at 46.3 degrees Celsius as a saturated liquid. Determine the rate of cooling provided by the system. B. The COP. C. The entropy generated in each component of the cycle. And D. Compare the COP with the Carnot cycle efficiency. So what we have is a R134A refrigerant. This is the vapor compression cycle of this in a TS diagram. So at 1 we have saturated vapor, and this is at minus 10 degrees Celsius. So the corresponding pressure is 140 kilopascal, and the flow rate is given as 375 liters per minute, and the compressor efficiency is 80%. And what you know is the condenser pressure is saturated pressure corresponding to 46.3 degrees Celsius. So let's see how to solve this. So first is we need to estimate each of the state points. So at state point 1, so the mass flow rate of the refrigerant is mass is volume flow rate divided by the specific volume. So specific volume is corresponding to the saturated vapor of 140 kilopascal. So pressure is 140 kilopascal, it is given here, and minus 10 is the room temperature, but we will be much lower than that temperature, because if you want to cool the room, the evaporator the medium which is providing cooling should be at lower temperature, or there will be no heat transfer. So we are at 140 kilopascal. So 140 kilopascal and vapor quality of 1 gives you an enthalpy of 239.17 kilojoule per kg, your entropy of 0.9446 kilojoule per kg Kelvin, and a specific volume of 0.1402 meter cube per kg. And what we know is, we know the P3 is at 43.6.3 degrees Celsius saturated liquid. So that will give you the operating pressure, the higher operating pressure, which is the saturated pressure corresponding to 46.3. So that gives you a pressure of 1200 kilopascal. So P2 is 1200 kilopascal, and we know if we consider an isentropic process, because the compressor efficiency given, so we have to find out first what is the isentropic case. So S2 is equals to S1. So that gives you an enthalpy of 284.09 kilojoule per kg. So after interpolating, this is what we get. So 284.09 kilojoule per kg, and the state point 3 is a saturated liquid. So we can straight away get the value. So corresponding to 1200 kilopascal, enthalpy is 117.77 kilojoule per kg, and similarly entropy is 0.4244 kilojoule per kg Kelvin. So H3 is equals to H4. So we'll get straight away. So at H4, we know it is at pressure of 140 kilopascal. So corresponding to 140 kilopascal and an enthalpy of 117.77, we get entropy at state 4 to be 0.4674 kilojoule per kg Kelvin. So we know now each of the state points, but what we don't know is at state point 2, we know 2s. So we know that compressor efficiency is 80%. So substituting that, compressor efficiency is isentropic work by the actual work in case of compressor. So 0.8 is the compressor efficiency is equals to 284.09 minus 239.17 divided by H2 minus H1. So that gives you H2 of 295.32 kilojoule per kg. So now we know enthalpy, we also know pressure, which is 200 kilopascal. So corresponding to these two state points, we can estimate entropy, and entropy comes out to be 0.9738, so 383 kilojoule per kg Kelvin. So now we have found out each of the state points corresponding enthalpy and entropy values. So now we can find out what is the mass flow rate and find out how much is the heat transfer and the work transfer which is happening in the cycle. So the mass flow rate of the refrigerant is the volume flow rate divided by the specific volume. So volume flow rate is 0.375 divided by 60, which is given as liters per minute, 375 liters per minute. So 1 liter is 10 power minus 3 meter cube, so 0.375 meter cube divided by 60, that gives you in meter cube per second, divided by your specific volume, which is 0.1402. So that gives you a mass flow rate of 0.04458 kg per second. So now the refrigeration load is H1 minus H4 into mass flow rate, which is the cooling provided here, H1 minus H4. So QL is m dot H1 minus H4. So substituting the values, m is 0.04458 multiplied by H1 is 239.17 minus H4 is 117.77 kilojoule per kg, gives you a cooling load of 5.41 kilowatt. And similarly the heat rejected, so heating is m into H2 minus H1 H3, so that gives you a value of for 7.92, which is kilowatt is the heat rejected to the ambient. So this is the heat cooling provided or the heat absorbed from the cooling space, the space which has to be cooled, so that is 5.41 kilowatts, and the heat which is rejected to ambient is 7.92 kilowatts. So the work done for in the cycle is to provide this cooling is m dot into H2 minus H1. So substituting the enthalpy and mass values, which get a work done of 2.5 kilowatt. So the COP of the cycle is, so here our desired output is the cooling requirement to cool the room to minus 10 degrees Celsius. So COP is the cooling load divided by the work which is provided, say input. So QL is 5.41 and W is 2.5. So substituting we get COP of 2.16. So since we have found out the COP, next is we need to find out what is the entropy generated in each of the component or in each of the process. So first is for the compressor. So we know the ambient is at 22 degrees Celsius. So 273 plus 22 gives you a dead state temperature of 295 Kelvin, which is the you can say the ambient or source temperature. So entropy generated at process 1 to 2 is your straight away mass into S2 minus S1, since there is no heat transfer. So the Q by T terms is 0. So what you get is the entropy generated is m dot S2 minus S1, and since we are consider all to be a steady state process, so your ds by dt term is also 0. So what we get is entropy generated straight away your entropy difference. So 0.04458 multiplied by the entropy at state 2 and minus state 1, so that gives you entropy generated to be 0.001502 kilowatt per Kelvin. So this is entropy generated in process 1 to 2. And similarly for the condenser, so in case of condenser you have both heat transfer, so and the flow rate entropy coming in and going out because of the flow rate of the refrigerant. So since it's a steady state, ds by dt is 0, so entropy generated is nothing but m dot S3 minus S2 plus QH by TH. So QH is we have calculated is 7.92, and this is getting rejected to the ambient. So the ambient temperature is at 22 degrees Celsius, which is 295. So substituting that we get mass flow rate is 0.04458 multiplied by the entropy difference plus 7.92 divided by 295, that gives you entropy generation in process 2 to 3 to be 0.002138 kilowatt Kelvin. Next For the expansion valve, so entropy generated is 3 to 4 straight away, because there is no heat transfer in steady state, so dS by dt is 0. So entropy generated to 3 to 4 is m dot S4 minus S3. So substituting, get 0.04458 multiplied by your entropy difference. So that gives you 0.001916 kilowatt per Kelvin of entropy generation in process 3 to 4. In case of evaporator, that is heat addition and not heat rejection. So here we get Sgen is m dot S1 minus S4 plus QL by TL. So whatever cooling space is, that is rejecting heat to the cycle. So QL is minus 5.41 in from the perspective of the room, divided by the room temperature, which is minus 10 degrees Celsius. So 273 minus 10 is 263. This plus m dot into S1 minus S4. So that gives you an entropy generated to be 0.0006964 kilowatt per Kelvin. So now if you compare the COP, the Carnot COP is your TL by TH minus TL, and TL is minus 10 degrees Celsius, which is the room temperature, and TH is your ambient temperature. So substituting the values, you get COP of Carnot to be 8.22, but what we see is our COP is 2.16. So if you see the ratio, which is also the second law efficiency, if you say, so COPO by COP of Carnot, so that comes out to be 26.3%. So this says that the actual efficiency, if you consider it to be 100%, which is the maximum efficiency which you can get, we are only at 26.3%, or we are close to 1/4 of the Carnot COP. This is the maximum ever efficiency which you can get, the COP which you can ever get, but we are operating at much lower, 26.3%. So this is the comparison which is given. So with that, we have finished the vapor compression cycle problems. So we'll have a recap on the topics which was covered in the engineering thermodynamics course. So start with the basics. What is the system, surrounding and boundary? So the system is whatever we want to study. So whatever is your objective of study, so that is a system. So it can be a shape or volume of the system being analyzed. So this is not necessarily constant. So if you see the system may the shape may change or vary based on what you consider to be a system, like a open system or closed system. So if you are considering in a piston cylinder arrangement as the compressor as a whole as your system, so your gas is coming in and going out, so there is no change in any shape or something. But if you are considering the gas to be your system, so the volume of the gas is getting compressed and expanded, so there is a change in volume and or shape. So it ultimately comes down to what you are considering and what you are trying to analyze and study. So that is your system, and everything except this, so whatever is out of your system, so that is your surrounding. And boundary, which is separating these two, system and surrounding, that is your boundary. So and then you have this type of system, this closed system, an isolated system, and a open system or a control volume. So controlled closed system is also called as a control mass system, where your mass remains same. So example is as we saw all the piston displacement problems. So there it's an closed system or a tank with just the mass, some gas filled in. So that is your closed system. So this closed system has, there is no mass transfer, so that is a closed system, and there can be heat transfer, so based on what kind of system is it, whether insulated or not. So then you have a control volume. So in case of a control volume, what happens is an open system, you have both mass transfer as well as energy transfer. And then isolated system is a special case of closed system, when you are insulating this closed system and there is no work transfer, nothing goes out of the system. So in that case it's an isolated system. So your whole universe is a isolated system, it's an example. So nothing goes out of the universe, right? Everything is encapsulated in the universe itself, so nothing lies outside, so there is no interaction outside the universe boundary. So it's an isolated system. So then property, so property is a macroscopic characteristics of a system. So like the examples of mass, volume, energy, pressure, temperature, so all case of property. So where you is easy to characterize the system based on the behavior and so on. So that defines, you are able to specify a location or a state, so it's useful for that. So the word state refers to the condition of the system, so how this, what the system is. The example, you are at second floor, you are at the first floor, so you are there is some description about the system. If you are considering yourself as a system, at what level you are in the building, and what state are you running, so it's kind of description of the system current position. So that is your state, and the way the state changes, or the path in which the state changes, that describes your process. And so the variation of this changes in the state in the system is called as a process. And then the system can be called as a steady state when you know that it's not changing with respect to time, so that is called as a steady state. And then we saw the problems on steady state flow energy equations and so on. Now the property itself can be of two types. So it can be an intensive property and it can be of an extensive property. So extensive properties are dependent on mass, and intensive is independent of mass, to be in general. So how do you know whether a property is an intensive or extensive? So you take some property for a system, you divide the system into pieces. So for example, you take 1 kg of water, you split it into two parts, so half kg, or so whatever proportion you want to be. And if you observe the property to be different for each of the parts, then it is an extensive property. If it doesn't change, even if you split it into two different parts or multiple parts, then it's an intensive property. So for example is the density. So if you split the water into multiple parts, the density will still remain same unless you go into some microscopic system. But if you at a higher macroscopic point of view, we are splitting into different parts, the density remains same, so that is your intensive property. And extensive, the volume or mass, so that varies in how you're spreading or the proportion you're spreading, the value will change. So mass, volume and all is your extensive property. And similarly, temperature, if you take, the temperature will also not change, because if you take hot water, split into two parts, the both individual part will have the same temperature. So it's an intensive property. So next is these are examples of different kinds of system and surrounding which we saw. So first is a closed adiabatic without work, and similarly other types, open adiabatic without work, open adiabatic with work. So these are different kinds of systems which you can come across. So closed non-adiabatic with work. So here you have closed, there is no mass transfer, it's a non-adiabatic, so it's heat transfer, and with work, so you have work transfer. So in the second case, it's open case, so it's adiabatic, there is no heat transfer, but there is also no work transfer, but there is a mass transfer. So it's a different kinds of system which you come across. Then example of a reciprocating pump, a piston compressor engine. So how a system is considered and so on. So this is the example which you saw for type of system. So you have a cup of hot tea. Here you have both heat transfer. Hot tea is being cooled by the surrounding. So you have heat transfer as well as some amount of water is evaporated. But you see steam which is coming out from the cup when you take a hot cup of tea. So there is mass transfer. So when you close this cup of tea with a lid, so now you are not allowing the mass to escape. So this becomes a closed system, but in this case also you have a heat transfer. So this is a closed system, control mass system. So previously it was a control volume, then it become a control mass. It's a open system, closed system. Then if you're pouring it into a insulated flask or a thermos flask, what happens is you are now not allowing the mass to escape as well as the heat to escape. So there is no heat transfer, there is no mass transfer, there is no work transfer. So this becomes an isolated system. And then we saw how any big process can be made into a small system kind of thing, and we just take note of the state of the system and what kind of mass or energy is coming in or going out. So any big process can be converted into a system, and the components of energies and mass flow rates, and it will become easier to analyze. So this is a big energy gas power plant which is generating electricity. So whatever coal is there, you are burning that coal and converting into steam and running a turbine, and then a part of the turbine is used to because it is a high temperature, you're using to district heating, and the turbine is running a generator, just generating electricity. So this is the whole concept, and that we have simplified it to the whole power plant as a system, which is a black box. We don't know what is happening inside, but we are concerned with just what is coming in and going out. So what was coming in is the cold water and the hot water which is going out for the district heating, and the electrical work which is coming out, and the air and flue gases which is coming, and cold which is coming in. So this is a whole simplified version of the power plant which can be made from through an energy balance or the analysis of the system. So next is the concept of equilibrium and process. So equilibrium, so state of system in which properties have definite unchanged value. So that is called as you are not, there is no change, even if the small change, it comes back to it. So you have three kinds of mechanical, thermal and chemical. And then process. So process is the change of the system undergoes, so the path in which the process undergoes. So it can be either a cyclic process where the start point and end points remain same, so that is also called as a cycle. And then your quasi-equilibrium process, so where you assume that the process is happening very infinitesimally small because of the unbalanced force. So you assume the process for reversible case, we assume it to be very infinitesimally small changes in the system occurring, and it's called the quasi-equilibrium. It's a near to equilibrium process. because non-equilibrium, it can go through any kind of process. We assume a simpler case because we are concerned with the end state points. So we assume it to be a quasi-equilibrium process. So then the heat and work. So what we assume is heat is positive when heat is transferred from surrounding to the system, and heat is negative when heat is transferred from the system to the surrounding. And then work is positive when the system does work on the surroundings, the opposite of heat. So when work is produced from the system, it's positive. When work is supplied to the system, it's negative. It's the other way around for heat. Heat supplied is positive and rejected is negative. And then we saw reversible, irreversible, and quasi-reversible. So reversible is if you are able to come back from the end state back to the initial state, then it's a reversible process. So an actual process cannot be reversible because of various reasons. Because of it can be a heat transfer, because heat transfer generates entropy, which you have seen, so which is irreversible. Then we have unrestrained expansion, because unless you do some work, you cannot bring it back. And then friction, so you have to do some work to overcome this friction. And then mixing of two different molecules, which this molecule cannot be easily separated, so you have to do some work to separate it out. Then heating by passing of electric current, so these are all or inelastic deformation, so these are all irreversible kind of process. So it can be irreversibility can be categorized as internal irreversibility and external irreversibility. So if this irreversibility occurs within the system, it's called as internal irreversibility, and if it occurs outside the system, that is in the surrounding, it's called as external irreversibility. And then we come to the laws of thermodynamics. So the first is the zeroth law of thermodynamics. So if two bodies are in contact and they are in thermal equilibrium, and the two other bodies are in similar thermal equilibrium, so in the first and third body will also be in thermal equilibrium. So it says the temperature. So it also says the other way of understanding is that there's a property called as temperature. When all three bodies are in same temperature, it is a necessary and sufficient condition which says that it is in thermal equilibrium. So then we saw first law of thermodynamics. The change in energy of a system is equal to the difference between the heat added to the system and the work done in the system. This is basically the energy transfer. Whatever energy is coming in and energy going out, so the energy is form of heat and work which is being crossing the boundary. So we are concerned only with the boundary. So for the system, so energy coming in and going out is equals to the energy change in the system. So that is given by the internal energy, so which is delta E. So when we assume that the potential energy and kinetic energy of the molecules or the chemical energy and other kinds of energy is constant and doesn't vary, then we can write it in terms of the internal energy. So delta U is Q minus W. This is for the closed system. So the property which we get is Q is a dependent on path, and W is also dependent on path. So it varies with the different process which is you are taking. So from 1 to 2, if you are taking three different kinds of paths or processes, so your Q and W will change for each of the process. But what will remain same is your delta U, because it only depends on the state. So even though Q and W are path dependent property, delta U is independent of path, which depends only on state. So it's an exact differential, and this is inexact differentials, Q and W. And then the mass balance, the conservation of mass. So for an unsteady flow rate, we get dm by dt equals mass in minus mass out. In case of a steady flow case, what happens is there is no mass accumulated. So whatever mass is coming in minus mass goes out is the mass accumulated or reduced in the system. So that is your unsteady case. So in steady flow, this mass accumulation or reduction is not there. So dmCV by dt. So because it is irrespective of time, so dmCV by dt is 0. So we get mass coming in is equals to mass going out in case of steady flow energy equation, steady flow process. And for conservation of energy, similarly, the energy coming in minus energy going out equals to the energy accumulated in the system. So the energy, total energy, if you see, is if you are also have mass balances, so rate of heat added minus rate of work done plus rate of energy flow which is into the system and minus rate of energy flow out of the system, and the mass which is coming in also carry some amount of energy. So it is written in terms of enthalpy. So what we get is dECV by dt equals QCV minus W plus M inlet flow rate Mi into Hi plus kinetic and potential energy. Similarly, minus exit stream energy minus Me He plus similarly the kinetic and potential energy. So in case of steady flow energy equation, we assume that this does not vary with respect to time, and the time dependent terms varies. So that is dCV by dt becomes 0, and what we get is Q minus W is mass into the enthalpy and kinetic and potential energy difference between the inlet streams and the outlet streams. So examples of some of the first law of thermodynamics is so a tank filling. So your empty tank, you are filling with some gas, so that is also an unsteady process. So in this case again if you see, there is some mass is coming in, so which is dm by dt is Mi, so which is the mass flow rate coming in. So that is the rate of change of mass in the system, and the rate of change of energy balance, if you see you get dE by dt is the energy coming in, so there is no Q and W which is happening, so it will be equal to Mi Hi. So Mi is dm by dt, so you get du by dt equals dm by dt into Hi. So that's an example of a tank filling, and then rocket nozzle. So in this case, if you see here, so there is some in the nozzle, there is some, if you assume it's insulated and there is no Q and W, so this will become 0, and in case of nozzle, so your enthalpy in plus the kinetic energy and potential energy at inlet is equal to the enthalpy plus kinetic and potential energy at the outlet. So what you get is C is 2 times Cp Tc minus Te. So if you assume it to be an isentropic expansion, so we can write PV raised to power gamma in terms of temperatures. We get Te by Tc equals Pe by Pc raised to power gamma minus 1 by gamma. So we can find it in terms of pressure ratios as well. So then comes the second law of thermodynamics. So we have in second law of thermodynamics, we have two statements. One is the Kelvin-Planck statement and other is the Clausius statement. So the Kelvin-Planck statement says that no process is possible, so whose sole result is the absorption of heat from a reservoir and the conversion of this heat into work. So what it says is there cannot be a process where it takes heat from a single source and then converts the all of heat to work. So this becomes your perpetual motion machine, and this is not possible, so that violates the Kelvin-Planck statement. And then the second is, so this is the Kelvin-Planck statement diagram. So you have a source where you are taking heat and converting all of the heat to work without rejecting to a lower temperature source. So that is your violation of Kelvin-Planck statement. And then the second statement is the Clausius statement. So he says that no process is possible whose sole result is the transfer of heat from a cooler to a hotter body. So that violates your Clausius statement. So without work transfer, you cannot transfer heat from a low temperature source to a high temperature source. That's what the Clausius statement says. And then you have Clausius inequality. So for a cyclic integral, so del q by t will be equal to 0 for a reversible process, and which is less than or equal to 0 for in general. So it will be less than 0 for a irreversible process. So violating any of one of the laws will also violate the other law statement. So if you violate Kelvin-Planck statement, it will inevitably violate the Clausius statement as well. So both are dependent. So that exists for every system in equilibrium, a property called entropy, so which can be written as dc is dq reversible by t. So your delta S total will always be greater than or equal to 0. So this is from the Clausius statement. So del q by t, if you write it as delta S, what you guess is delta S is always greater than equal to 0. So then you have entropy generation or entropy balance. So you get ds is del q by t plus entropy generated. So in case of ds, so this is from the Clausius inequality. If you see, for reversible process, ds is dq reversible by t, but in irreversible process there is some additional entropy which is generated. So because ds is always greater than or equal to 0, to make it 0, what we write is ds equals dq by t plus some entropy generated term. So and that's what we get, and expanding it to a process, for flow process, we get summation of qc by t, which is the addition of all the heat transfers which is happening with respect to the sources temperature, plus your inlet stream entropy which is coming in minus the exit stream entropy, plus the entropy generated is equals to the change in entropy of the system with respect to time. So this is your entropy balance. And then we have Carnot cycle. So we know Carnot cycle, which has two isentropic compression, then reversible isentropic compression, then isothermal compression, then isentropic expansion, and then isothermal expansion. So you have 4 processes, and then it's a reversible process. So if you solve it, so because it's a reversible cycle, we can apply the Clausius inequality, and because integral del q by t equals 0, so you have only 2 processes where there is heat transfer which is happening. So which is the heat transfer in the isothermal case. So it becomes q1 by t1 plus q2 by t2 equals 0, and then a little bit of rearranging, and efficiency will get 1 minus t1 by t2, which is the Carnot cycle efficiency. And similarly, the isentropic efficiency for turbine is your actual work output of turbine divided by the isentropic work output. And in case of compressor, it is the other way around, which is the isentropic work divided by the actual work in a compressor. And we have different kinds of process based on the property. So if you have pressure which is being constant, then it's called an isobaric process. So in that case your pressure remains constant, and then isochoric process where your volume or density remains constant, and then isothermal process where your temperature remains constant, and then isenthalpic process where your enthalpy remains constant, then isentropic process where your entropy remains constant, adiabatic process where your q is 0, and an internally reversible process or an reversible adiabatic process. Then another this thing is an isentropic process where your entropy is 0. And this is your Carnot cycle, which you have seen. So you have 4 different processes. You have isentropic compression from 4 to 1, and then 1 to 2 isothermal heat addition is also an isothermal compression in some books you can see. And then because here there is both heat transfer and work transfer, and then 2 to 3 is your isentropic expansion, and 3 to 4 is your isothermal heat rejection, and here also because it's isothermal you have both heat and work transfer. So we also saw why Carnot cycle is difficult to achieve, and what is the problem with generating the processes and so on, and the total capital cost which happens and so on. And then q1 by this is the process and cycle efficiencies for Carnot cycle. And then comes your Brayton cycle. So you have open cycle and closed cycle. You have isentropic compression and then isobaric heat addition and then isentropic expansion in the turbine. And in some cases, if it's a closed loop, then there is a isobaric heat rejection, and then it goes back to the compressor. So you have isentropic compression A to B, isobaric heat addition, and then C to D isentropic expansion, and the D to E isobaric heat rejection. So in this case, because isobaric isentropic process, so your pressures BC and AD remain same. So you have some pressure ratio. So using that, you can also find out the temperature ratios here, because P to C, B to A, and C to D are isentropic processes, which is reversible adiabatic. So which is PV raised to gamma. So that can be written in terms of pressures and temperature. So the other way of writing Brayton cycle efficiency is 1 minus Ta by Tb, which can be written in terms of pressure ratio. And then we also saw of for pure fluids when it exists as vapor and liquid, how to calculate each of the properties and so on using the quality. And the quality is your mass of vapor divided by the total mass. That is your quality. And then comes the Rankine cycle. So the Rankine cycle consists of isentropic compression or pumping, so from 3 to 4, and then heat addition. It's an isobaric heat addition 4 to 1, and then 1 to 2 isentropic expansion, and then 2 to 3, which is isobaric heat rejection. So this is similar to Brayton cycle. Only thing is it operates inside the vapor dome, where and here it's the pumping happens as a liquid. So the work done in case of pumping the fluid to a higher pressure is negligible, because work done is V delta P. So your specific volume of liquid is much low compared to gases. So your work done in case of pumping the fluid to higher pressure is lower for Rankine cycle compared to a Brayton cycle. Otherwise the process remains same. The only change is the Brayton cycle operates as a gas power cycle, and this is your vapor power cycle. So you can estimate each of the process heat and work done, which is just the change in enthalpy, and then we can find out the efficiency. So you can find out as W by Qin or 1 minus Q out by Qin, and then the back work ratio is how much of the work is used for compressing or used by the cycle compared to what is produced. So the pump work divided by the turbine work. And then we also saw how the effect of changing the pressures and temperature affects the efficiency. And then we have vapor compression refrigerated cycle, so which we saw today. So we have isentropic compression, and then isobaric heat rejection, and then isenthalpic expansion, and then isobaric heat addition. So that is your vapor compression cycle. And then last we also saw some problems on mixtures. So your moles are generally written as mass by the molar mass. So that gives you the mole of system, converting mass to mole. And the mass fraction is nothing but the mass of the species divided by the total mass. And we know that sum of all the mass fractions will be equal to 1. And similarly the mole fraction is your mole of that species divided by the total mole. And similarly the mole fraction, sum of mole fractions also 1. So the total molar mass of the mixture is your mole fraction multiplied by your molar mass. So that gives you the molecular weight of the mixture or the molar mass of the mixture. And we also know the partial pressure of individual species is equal to your mass mole fraction multiplied by the total pressure. That gives you the partial pressure, and the sum of partial pressures will be equal to the total pressure, because P will be constant. So it will be summation of yi. So summation of yi is 1. So we get p. And similarly the other properties like internal energy, enthalpy and entropy can also be found out using multiplied by corresponding mole fraction multiplied by the corresponding molar internal energies or enthalpies. It all in molar properties. And if it is in mass properties, we have to multiply by the mass fraction. So with that we have covered what is covered in the engineering thermodynamics course. And with this it ends the problem solving session, and I have covered all the problems and the topics in general, a brief introduction to the topics, a recap to the topics. So with that we come to the end of the session. So thank you and all the best for the exams. Close the session. Thank you for joining and all the best.